Hello TGS 300 and welcome back to what's going to be the third laboratory session so far for quantitative methods for spatial sciences. So today what we're going to be doing is we're going to be calculating some of those spatial descriptive statistic techniques that we carried out kind of theoretically within the lecture, but now we're going to basically have a go at tapping out some code within an R script in order to generate some of those metrics manually, and also using some of the kind of built-in functions that R has within its toolbox. So hopefully you'll be able to download this code now using the Blackboard website, and make sure that you open the code along with the data that's available there, and then hopefully you'll be able to get this this laboratory session started. Okay, so this should all be fairly familiar to you now. So being able to install the RStudio RPI, basically get the directory name for the folder that you're in, and then basically set the working directory as the folder that you're working from. Okay, so that should be fairly easy for you to carry out. So here, sorry, I'm able to get my folder in the global environment, and I'm able to allocate folder to set working directory so that we have that set for the file which we're in, sorry, the folder which we're in. So you'll remember within the actual lecture we covered a variety of different spatial techniques. So if I just recap to where we got to, we covered spatial measures for central tendency, dispersion, both in terms of absolute and relative terms. Okay. What we're going to do today is we're going to load in some data sets which I provided to you, which are just some spatial data points for baseball teams for the year 1900 and the year 2000, and then we're going to basically carry out some of those spatial descriptive techniques on those data sets. So while there are many multiple methods for spatial central tendency in R, we're going to focus on the mean center and the two ways in which we can calculate distance, so the two distant methods that we can use for central feature through the use of a loop. There will be a consequential laboratory session which will focus on using ArcMap to carry out some of those spatial statistical processes. So today we're just going to focus on those two aspects which I just mentioned. So let's load the data for those two different data sets, which provide us with attribute tables giving the location of Major League Baseball teams for 1900 and 2000, and we can see how the mean center has shifted over time. Okay, so you should be familiar now with read.csv, so how you basically use this function to load in some CSV files within the working directory that we're operating in. And you can basically load both of these in and take a look at the data. So for this one, which has 8 observations for 7 different variables, we have the 1900 teams, so for Boston, Brooklyn, Chicago, Cincinnati, New York, Philadelphia, Pittsburgh and St. Louis, the state identifier, the latitude, the longitude, and then we also have X and Y coordinates as well. Okay. So essentially that's going to be, these longitude coordinates here will be unprojected and will be in degrees, and these coordinates here will be projected and will basically be in probably meters, I suspect. But today we can just get along with using the latitude and longitude coordinates. So let's have a go at getting the mean center. So when you look at the tables, you'll notice that we have both of those different types of coordinates in different coordinate reference systems. Okay, so you can use both of them to calculate the mean center. Let's use the lat long here, but you can still use the xy later in order to get the distance in a projected coordinate system, so producing meter distances, for example. So to calculate the mean center, you must first find the average for the x coordinate and the average for the y coordinate. Okay, so we can actually just do this by taking the column which we're referring to, which here is in the baseball for 1900 dataset, and then the latitude column, and just providing it to that mean function that we've used previously. So you should be familiar with this now. You can still do a search to look at the arithmetic mean function in the help menu if you want, but we can just allocate those means for latitude and longitude for 1900 to these two different variable names here, so mean latitude, mean longitude, and put them in the global memory, and we end up with 40.48036 degrees and minus 79.54686 degrees. Okay. So baseball's year 1900 mean center as follows. So for those different means that I just presented. So for the year 2000, we're going to be working in decimal degrees again, and we're going to use the latitude and longitude from the BB20, so the baseball 2000 data set for the 20th century. And what we get is a very different set of mean centers, okay? And obviously it's not very nice just to kind of look at these numbers as they are, although that can be kind of useful sometimes, but we can actually plot these on a map to show where they basically show over time. So if we just plot the longitude and latitude for the year 2000, we get this type of very basic kind of plot. It's not very nice, but we can use the points function to actually add points on top of the existing plot for 1900, okay? So when we do that, what we can do is we can say, for the year 2000, plot all the points, which is what we did, and then for the year 1900, plot those points over the top using a point character, a PCH of 2. I can't remember what that stands for. I think it's the shape of the characters here. So it's basically saying give us item 2, which in this case I think is a triangle. And give us the color 2, which is basically red, okay? So it's able to present those results plotted on top of each other, but it's kind of meaningless, right, without actually having a decent map behind it. So we can plot the mean centers as well if we want, so we can use the points function again to plot the mean center for the red triangles, which is 9 for 1900, and the mean center for the black circles, which is 2000, okay? So you can have these different mean centers plotted on this map. I don't really like this. I mean, it's not very pretty, it doesn't really look very nice, so what I suggest you do is install ggmap, as I've shown here, and then actually load it into your memory. And then once you've done that, what we can do is we can basically plot it using a really nice fancy data package, okay, and it will make a really nice map. So what we need to do first is we need to basically combine into a single data set our two different data sets, okay? So we have the 1900 data here and the 2000 data here. What I'm going to do is I'm going to add a new column called year and allocate it for BB19. I'm going to allocate it 1900, and for BB20 the year column is going to have 2000, okay? So that's going to add a new variable here. So see, when I press Control Enter, you can see that went up to 8 variables because I added this new variable on the end of this existing data frame. And then once we've got those two different data frames, what we can do is we can basically do what's called an R-bind, which stands for row bind. So you can go help R-bind like this, and you can see the function that we're about to use. So using cbind or R-bind, you can combine our objects by row or column. And here what we want to do is we want to take the two different data sets and we want to do a row bind like this. So basically it's a vertical concatenation. So you're able to just stick these two data sets together. So if you don't understand what that means, run this code rbind for the two different ones, and providing the columns are matching, you'll be able to create this new object called all data. And you can see here what we've done is we've managed to integrate those two data sets into a single data set. So we have the first set of data for 1900, ID'd up to 7 here. And then we have the next set of data which lists 2000 as the year, okay? Great, now we've got that, we can also create a data frame out of our mean data. So for the year, so what we can do is we can take the longitudes like this, which is where we concatenate the mean for the longitude for 1900 and the mean for the longitude for 2000. And that adds this longitude up here in degrees. And we can do the same for latitude, and we can do the same concatenate for year. So we have these three objects, long, lat, and year, and we can just use the data frame function to basically stitch them all together into something called a mean data. Something called mean data. Okay, so this is what the shape of the data frame is. And the reason why we're doing this is that now we can actually provide the data frames that we've just produced to this function that's going to create us a really fancy map. Okay, so we're going to plot using qmplot. We're going to provide it with the latitude and longitude, so the longitude and latitude columns. We're going to specify that the data is for the all data data frame. We're going to specify the map type, which is toner, background, and the color. Okay, and that will basically give us a pretty map. But then we're also able to do something called facet wrapping. So basically that means that we're able to say, plot multiple different maps based on the year. Okay, you see that this is the year column here, and that allows us to plot more than one map with the different year data plotted in different ways. And then finally, what we were able to do is we were able to create a new geometry point layer out of the longitude and latitude coordinates for the mean data. Okay, so that's quite a bit to stitch together, but let me show you what it produces, because I think you'll be impressed with the results. So what we have here is a map for 1900 with those baseball team locations and the mean centre for 1900. And then we have a similar map here for 2000 where we've got many more baseball team locations, and we've got the mean centre listed here, which is on top of Missouri. I think that's Missouri, sorry. My US geography as we get into the middle of the country sometimes can be a little patchy. Basically over here we have the 1900 mean centre. So basically what we've had over 100 years as the population spread west and south in the United States, and as a consequence there have been more baseball teams popping up in all those different cities which are in other parts of the United States. It's pulled the mean centre to the west and to the south a bit, but this is just a nice way for us to basically plot that using a kind of fancy map. Okay. So the trick to get the two different maps is to have the facet wrap, as I showed here. Okay, great. Well, I hope you like that and that you're impressed with that function, because you can reuse them in your own research if you want to. You've got the code now. Let's move on to measuring the Euclidean distance. So you'll remember that we covered this within within the presentation which I gave in the previous lecture. And basically between two separate points, providing that we have a grid reference system, we can basically treat those two separate points as the hypotenuse in a right angle triangle. And then because we already know what these psi values are going to be, okay, by basically using the coordinate reference system which we have, and therefore using the Pythagoras theorem in order to get the distance of this hypotenuse here. So I think this is probably just repeating what I've already said. What I will say is that, okay, we're doing this here in degrees, so it would need to be converted into kind of a meaningful a distance measure, but you get the idea of basically what we're doing. Okay, so we're going to calculate the Euclidean distance between the mean longitude and latitude, so the mean centre for 1900 and the mean centre for 2000. Okay, so it's this distance between these yellow squares, diamonds. Great, so it is this equation here. So dij equals, and it's the square root of this outcome. So you're subtracting xj from xi, squaring it and adding it together with the outcome of this part of the equation for the y coordinates. Okay, so if we do that, and that's a fairly straightforward equation for you there, I've written it out. So we're subtracting the longitude for 2000 from the mean longitude for 1900. We're then squaring this, and then we're adding it together against the latitude versions of these means, okay, and taking the square root. So we get 13.00991 degrees difference, okay, based on this change in the mean centre of these baseball team changes over time. Okay, great. So you can convert that if you want into a kind of a real distance measure. So if you basically redo this and you use the xy coordinates which are in a projected system, then you should be able to get a meaningful measure for distance. We can also calculate the Manhattan distance, and you'll remember that I kind of went off on a tangent to explain that there's multiple different types of distance that we can use. So the Manhattan distance, rather than taking this hypotenuse distance between Chicago and Columbus, you can take the Manhattan distance. So this is basically the two sides of that right-handed triangle, and as a consequence, you just need to subtract the xi and the xj coordinates here to get this distance. This distance here on the x-axis, and the yi and the yj to get this y distance here. And then this would present the distance that you would travel if you went along that Manhattan distance there, okay? So the way that we do that is we find the absolute of the outcome from subtracting this longitude and this longitude for 2000 and 1900, and then adding it to the absolute for the same versions for the latitude, okay? And when we do that, we get 14.85104 degrees, okay? So that's the mean center distance shift via the method of Manhattan distance that we've used here. So in terms of spatial measures of dispersion, remember that as with central tendency, there's multiple methods for measuring this level of dispersion spatially, and we're going to focus here just on the standard distance, okay? So let's calculate that metric for each baseball year, and this allows us to know the absolute dispersion in each. So the SD, let me find the slide here so you can see the equation. The standard distance here, the ST, is calculated by summing the square deviation from the mean. So you remember that we have the mean value here, this x bar, and it's subtracted from each one of the xi coordinates here. And then when we've got that deviation, we square it, okay? We'll do the same for the y coordinates as well. We sum them. So it's the sum of the square deviation from the mean in each coordinate, adding those sums together. And then eventually we divide by the number of spatial objects. So remember, this is the sample size, lowercase n. And then we eventually take the square root. Okay, so we're putting it back into the original units for the units which the original data were in. It's complex in one equation, so let's break it down. Okay, so for 1900 to get the standard distance, what we're going to do is we're going to get the sum of the square deviation from each coordinate to the mean center in each direction. Okay, so we're going to take the longitude column in our data set. So for 1900, we're going to subtract that mean value for 1900 for longitude. We're then going to square these deviations and then sum them up. Okay, we can do the same for the x and the y coordinate. And then when we've done that, all we have to do is we just have to add them together here and then divide by the number of data points in our data set and then take the square root. So when we run that back through, we get 6.798072. And obviously that's measured in degrees, so we would need to convert that to a projected coordinate system in order to get the kind of kilometre measurement for how much that's shifted. Sorry, not shifted, that's just the standard distance within that exact data set for the year 1900. And then for the year 2000, essentially what we're going to do is exactly the same processing. So we're going to subtract the mean from that mean center from each of the longitude values here for the year 2000. And then we're going to square them and then add them all up. Okay, so we're going to get that x20 and y20 set of parameters which are now in our global environment up here. So we can see that for x20 and y20. And then what we're going to do is we're going to do the same again. So we add them together to get the numerator, and then we divide them by the length of the total number of sample points that we've got, which is 30. And then when we take the square root, we end up with 17.26032 as the standard distance. So this is the standard distance is 17.26 degrees. And that's understandable, right? Because when we're in 1900, we don't have much spatial spread. There's 7 teams. It's mainly in the northeast and the kind of in kind of the Midwest area here. So basically, this isn't very spread out. Whereas by the time we get to the year 2000, we've got many more teams. So that standard distance has increased quite dramatically. Okay, so we went from 6.79 all the way up to 17.26. So that clearly means that people playing baseball are taking much longer flights in order to get to different destinations as a consequence. Great, so I hope this wasn't too arduous for you. I've given you the code for what's really some kind of very simple spatial statistical metrics which we've developed here, and I hope that the kind of snazzy code that I gave you to produce these nice looking maps will also be interesting for you, as you can use that in future research projects or other pieces of work that you might be working on, or even producing maps for future parts of this module if any come up. Great, well thanks for tuning in, and I'll look forward to seeing you all again soon in the next lecture. Thank you, goodbye.